Right, one way to define exponentials other than base e is if we take a that's positive and not 1, we can define a to the x to be e to the natural log of a times x. And we're going to be, then that's how we're going to come up with a rule for taking derivatives of bases other than e, exponential bases other than e. So d dx of a to the x is equal to the derivative of e ln of a times x. So that derivative will be ln of a and then e to the ln a times x. And what that amounts to is ln of a and then e to the ln a of x is just a to the x. Okay. So we just introduce an ln of a and times a to the x when we take the derivative. And then in general, if we have a and then some composite function u in terms of x, that's going to be ln of a times u prime for the chain rule, and then times a to the u. So we'll do a couple examples where we take some derivatives of bases other than e. So let's say we have f of x is equal to 2 to the 17x. So we take the derivative. It's going to be ln of the base times the derivative of the exponent, which is 17, times the exponential 12 to the x. We're just rewriting 17 ln of 2 times 2 to the 17 x power. So just take a little practice and get the hang of this. Let's try another example. And we have x squared times 5 to the minus 3x, so we're going to have a product. So the product rule is going to come into play. We might have to use a little bit of the chain rule because we have a composite of 5 to the minus 3x. So the derivative of the first function is 2x times the second function plus the first function times the derivative of the second, so that's going to be ln of the base, ln of 5. Derivative of the exponent is just negative 3, and then times the exponential. And then we're going to go ahead and factor out like terms. So like terms would be 5 to the negative 3x, and our leftovers are 2x minus 3 ln 5 x squared. And if you wanted to, you could factor out an x there. There's nothing wrong with doing that. I just decided I was going to package my answer like this. Okay, so pretty straightforward. Let's try another one. What do we got here? 5 to the alpha over 3, negative alpha over 3, and then sine of 7 alpha. So again, we have a product of functions, and we might have to use the chain rule, but this is fine. You can handle that. All right. So it's going to be ln of the base for the first function times the derivative of the exponent, so the derivative of negative alpha over 3. What world am I doing here? So if it was terms of x, then it would just be a constant. So we don't mean x here, we mean alpha. So let's fix that. In the excitement, we always write all kinds of crazy things. So when we go back and look at this, it should be in terms of alpha. Okay. Going back on, so it's ln of the base, and then times the derivative of the exponent, and that's going to be negative 1/3, and then times the exponential, and then times the second function. Then, because of the product rule, it's going to be the first function, and then times the derivative of the second, so it would be cosine 7 alpha, chain rule gives the 7. And then we will factor out what we have in common here, which is a 5 to the negative alpha over 3. Leftover is negative 1/3 ln of 5 sine of 7 alpha plus 7 cosine of 7 alpha. And maybe if you were doing a problem kind of like this in your textbook, they may have factored out the negative 1/3. That's perfectly fine, but you know, it'd be an equivalent derivative. We'd just be packaged a little bit differently. Okay, so pretty straightforward.